Welcome to part 2 of our Euclidean geometry course. And remember, in part 1 we covered just the basics, which is mainly the content that you covered in grade 8 until grade 10. So today we are starting with the business of your grade, which is grade 11. So we'll be covering theorem 1, which talks about the line from center. Let's dive into that real quick. Okay, so first of all, what we have is that the theorem states that, this is theorem 1a, states that the line that is drawn from the center of a circle perpendicular to a chord will bisect the chord. Remember, the word bisect, it simply means that cuts into two equal parts. So in general or practically, this is what it means. If you have a circle that has a known center, which is that right there, and you have a chord, remember we said a chord in our previous lesson, we said a chord is a line that is drawn from the circumference to the circumference, right? But doesn't necessarily go through the center. So when you have a line that is drawn from the center, which is usually denoted O, right, such that it is perpendicular to the chord, it will do what? It will bisect the chord. It will cut the chord into two equal parts. So if we have this as A, B, C, right, the conclusion that you can draw there is that the line AB is equals to BC, and the accepted reason for that, as you can see, it says that it's the line from center perpendicular to a chord. So each time you use this theorem, this is the appropriate reason to use. Okay, now when we speak of a theorem, basically we are speaking about a mathematical fact. It's a mathematical fact that can be proven, right? So we need to know a certain proofs on the theorems that we will uncover this year. The theorems that we'll look at, most of them have proofs. Like this one, we have to know the proof of this. So always whenever you are trying to prove a theorem, start by stating what you have required to prove. What are you required to prove? You are required to prove that AB is equals to BC. But what is it that you are given? You are given that OB is perpendicular to what? To AC. And then there comes the construction part. You need to construct something. So for the construction in this case, you are going to construct a line that runs from O all the way to A, and construct another line that runs from C all the way to O. So construct OA and what? And OC. Then you can go for the proof itself, right? And then this proof includes congruency. You're going to use congruency for this one. So you can call this one P1 and call that one P2. So the first thing that you can see is that the line which we just constructed, remember, before, whenever you use congruence, you first need to state your triangles. In triangle OAB, so this opening statement doesn't matter, like how you name the triangles in the opening statements. You can call this one OAB and call the other one OBC, triangle OBC, doesn't really matter, right? In your opening statement, I need to emphasize that. So the line OA will be equals to the line OC, as you can see, and that's a radii, right? Because we said radiuses, which in plural form, when you have multiple radiuses, it's called a radii, and they are all equal if they are in the same circle. As you can see, that's a radius and that's a radius. So those two are equal to each other. And then secondly, we have the line OP, which is equals to OP. As you can see, OP is a common line in both triangles. So this is a common side, right? And then lastly, as you can see, the angle B1 will be equals to the angle B2, and they will both be equals to what? They are both equals to 90 degrees, right? Or angles in a straight line will give you B1. Now let's check. We have proved this hypotenuse right here and that hypotenuse there, and we have proved the side. We have also proven the right angle, so we can make a conclusion. Now the conclusion part is very much important. Let's look at the first statement. We have OA, which means we can call this triangle OAB, right? And then we check this is congruent to triangle what? Look at which one you started with. You started with OC, so this is OCB. Why? Because of right angle hypotenuse side. You proved the right angle and the hypotenuse as stated in the previous video. And then if that's the case, the reason why the last part is important, the reason why the concluding statement is important, is because the first two letters, the OA, should be equals to OB. Sorry, should be equals to OC. First two is equals to first two, and the last two should be equals to each other, incongruence, which means AB should be equals to CB, like that. And then the first and last, which means whenever you take O and B, you should take O and B right there, as we've proved it. We used it on our proof. OB should be equals to OB from congruence. That's why the concluding statement is very much important. And also not only the side, but also the angles. Right, first angles, that angle O there and that angle O should be equals to each other. As you can see, we have O1 and O2 there. And then the middle ones, the angle A should be equals to the angle C, and then the angle B should be equals to angle B, as we had B1 and B2. Okay, so we are done proving that. Oh, remember we're trying to prove that AP is equals to PC. There we have it, AP is equals to PC or CP. So in conclusion, AP should be equals to PC. What's the reason? This comes from congruence, like that. Okay, now moving on. There is a converse of this theorem. Now you need to understand what we mean by a converse. Alright, converse 1a. If we say that like that and B implies A, what I mean by this, let's think of a scenario now, right? If A is an event such that you have eaten and B is an event such that you are full, if you have eaten, it means you are full. So A implies B simply means that if you have eaten, it means you are full, like that. And then B implies A, because the opposite should also be true. That's what a converse means. B implies A as well. It means whenever you are full, it means you have eaten. You see how it holds. So that's what a converse really means. And in fact, we will look into the converse shortly. Let's see that. This is the proof as we have done it. As you can see, there was a construction. So this proof is the one which we just did in the previous page. Let's quickly browse. Yes, this is the converse now. What does a converse mean? The converse tells us that the line drawn from what? The line drawn from the center of a circle to the midpoint of a chord is perpendicular to the chord. So A implies B, B implies A. We'll look at that shortly. Let us quickly do the proof of this theorem and then see the difference between the two. Okay, so right here we have a chord. Now remember, a chord, we said it runs from circumference to circumference and not necessarily through the center. And then we have a line that is drawn from center such that now they are not saying it's perpendicular, but rather it goes through the midpoint of that, which means it cuts those into two equal parts. So that's A, that's B, that's C, and then you have the center, which is O, right? So what this theorem allows you to conclude is that whenever the line is drawn from center to the midpoint of a chord, it implies that this should be perpendicular to that. So OB will be perpendicular to AC. Why? There's the reason. A line from center to what? To midpoint of a chord, like that, to midpoint chord. Okay, now this is another proof. This is another theorem which needs us to prove. Again, similar to the previous one, we had required to prove. What are you required to prove? You are required to prove that OB is perpendicular to AC. What are you given? Now you are given the opposite. You are given that AB is equals to BC. Remember, this is what you were trying to prove previously. And then again, by construction, you need to construct something whenever you prove a theorem. So even for this one, we are going to construct a line like that and construct a line like that. So we constructed OA and OC. Right, then you can name it whatever. This is B1, that's B2, that's O1, that's O2. And we go for the proof. Even this proof uses congruence. The opening statement, not so important in terms of the naming. In triangle OAB, if you like. But the normal way to name it, once you go from this side to that side, you should follow the same order as that. Right, so which means the other one should be triangle what? Triangle OCB. Should be triangle OCB. First things first, we can see the OA being equals to OC. It's the lines that we constructed that run from the center to the circumference, called the radius. So the radii in plural form, and they are equal to each other. Again, we have the line OB, which is equal to the line OB, and that's a common side, right? And then lastly, what is it that we have? We have the line AB, which is equal to the line BC, right? And remember, this is given to us, so that's what we have in all of those. So we've managed to prove that this is equals to that, and there's also a common side. Then we can go for our conclusion. The conclusion tells you like which sides are equal. So I started with OA there. Triangle OA, then the last letter there on the first triangle is B. Should be congruent to the triangle. There, OA corresponded with OC, so that should be OCB, like that. And this is side because we used sides to prove. And what does this mean? We spoke about it. We said in terms of the sides, it means the sides are all equal. Remember, we already proved the sides and the angles as well. So it means the angle O will be equals to angle O. So first and first, this one right here corresponds with that. Middle and middle, it means the A should be equals to C, right? Angle A should be equals to what? Should be angle C. And then lastly, angle B should be equals to angle B. Angle B is equals to angle B. Then we go to the triangles themselves. You can see that the first triangle contains O1 and the other one contains O2. There's nothing wrong with A and C, but the first triangle has B1, the second one has what? B2, like that. Okay, so we have proven that B1 is equals to B2. Then we can go ahead and say what? B1 plus B2 should give us 180 degrees. As you can see, those are angles on a straight line, right? Okay, but remember what we just proved. We just proved that B1 is equals to B2. And if B1 is equals to B2, we can just choose one of them, then return it to that statement. Instead of having B1 now, I'm just going to call that B2. So B2, remember this was replaced by that. So it's B2 plus B2, which gives us 180 degrees. As you can see now, it's 2B2. And in fact, B2 should then be equals to 90 degrees, which is equals to B1. And that's exactly what we were trying to prove, that there's a 90 there. And in conclusion, we have what? We have OB, which is then perpendicular to AC. Why? Because we just proved that B1 is equals to 90 degrees and B2. In fact, you don't even need a reason for that. I hope this makes sense. And you should know the difference. Let's just try to point out the difference between the two theorems. So we have our center there. Then line drawn from center perpendicular to a chord bisects the chord. Line drawn from center to midpoint of a chord is perpendicular to the chord. So let's call this one O, A, B, and C. Please wait. There you have it. One and its converse. Now, let's start with theorem 1. Remember, theorem 1 said if you have a line drawn from center perpendicular to the chord. So what are you given? In this case, you are given that OB is perpendicular to AC. And then what is your conclusion whenever you see that? Whenever you see that, you are going to conclude that, oh, AB is equals to BC. This is equals to that. And what's the reason? The reason is line from center to what? Line from center perpendicular to chord, like that. And then we go for the second one. The second one says that the line drawn from center to the midpoint of a chord is perpendicular to the chord, which means now you are given that this is equals to that. What are you given? You are given that AB is equals to BC. And what's your conclusion whenever you see that? Now you conclude that what? OB will be perpendicular to AC. And then what's your reason for that? This is this has to be line from center to what? To midpoint, mid PT of a chord. You see now that those two things are different, but they are opposites of one another. So that's our conclusion. In both cases, our conclusion is in red. So I hope this highlights, sheds some light. So that's where they've proved it. That's where you have it, right? Okay, let's move on from that. Now the problems. Whenever you want to work with theorem 1 and theorem 1a, always remember this. Pythagoras theorem. Always remember the Pythagoras theorem. These two theorems are so dependent on the Pythagoras theorem. So let's look at the first problem. O is the center of the circle. Then in this case, they want us to calculate OC. Find the length of OC. First of all, as you can see, what is it that we are given there? We are given the length of AC. We are given AC, which is equals to 8 units. And we are also given what? We are given OP, which is equals to 3 units. So our duty is to find the radius. But if you look at that, you have a line that is drawn from center perpendicular to a chord. We know our conclusion. What is our conclusion? That AB should be equals to BC, and in fact both of them should be equals to the half of 8, which is 4 units for each. But wait, what is the reason for that? We have a line drawn from center, so it's line from center, what? Perpendicular to a chord, right? And like I said, let's go back. Pythagoras theorem comes into action. Why? Because we have a right angle triangle. So let's reconstruct that so that you can see it clearly. We have this now, that triangle which looks something like that, then it goes this way. So there's your 90 degrees there, and then here you have B, you have C. We just calculated this, we got 4. You have O, this one was given to be 3. Remember how to identify your hypotenuse? Draw that diagonal. So as you can see, OC squared has to be equals to OB squared plus what? Plus BC squared. And what's that? This is the Pythagoras theorem. You need to have a reason. So OC squared, which is equals to OP, we can see that's 3 squared plus BC is 4. So that's 4 squared. So OC squared, which is equals to 3 squared, which is 9, plus that, which is 16. 16 plus 9, which is 25. So OC squared is 25. Then we square root both sides like that. Hence OC is equals to 5 units. Easy stuff, right? Let's move on. Let's look at another one. Okay, this is for you to do. Okay, but now it's actually the opposite. Calculate the length of AC, or maybe we should try it. Just gonna do one of these, and then the rest is yours. Let's take our A. Look at that. O is the center of the circle. You are given OB, which is 6 centimeters. Oh, now you, not centimeters, 6 units. You are given OC, which is equals to 10 units. OC is the radius, remember that. And OB is perpendicular to AC. There, line from center, perpendicular to a chord, which technically means what? We can already conclude on that, that the AB should be equals to BC. Why is that? Because we have a line that is drawn from center. So it's the line from center such that that line is perpendicular to a chord, right? So in conclusion, this is equals to that. Calculate the length of AC. But before we calculate AC, let's first find BC. There we have a complete right angle triangle. Again, Pythagoras comes into our rescue. That triangle looks something like that, whereby here we are given a 90 degrees, and then we have O, which is 10. There we have C, 6, and then we have B. Remember the Pythagoras theorem. First identify your hypotenuse, which is OC. Again, this is OC squared, which is equals to OB squared plus BC squared, which is what? Which is the Pythagoras theorem. And then from here we have OC. Where's OC? OC is given to be 10. So that's 10 squared. Do we have OB? Yes, OB is 6. So that's 6 squared plus BC squared. Then this is 100, and 6 squared, which is 36, plus what? Plus BC squared. Transpose that. So this is 100 minus 36. We should give us what? We should give us BC squared, which is 64. Therefore, BC, which is equals to square root this side, square root that side, which is 8 units. So you have BC to be 8 units. But wait, we just said something about BC being equals to AB. So by default, you can see that the line AC is equals to AB plus BC, which means it's going to be 8 plus 8. And that's none other than 16 units. See how this theorem works? Then we move on. Here's another one. One thing that you need to know and always remember is that when it comes to theorem, when it comes to the radius or the radii, look at that circle, that given circle. This radius right here, OA, will be equals to that radius there, which is OD, and in fact will be equals to any imaginary radius that you can think of. Will be equals to the one on OC, will be equals to the one on OP, even though it's not constructed, as long as it's the same circle. So let's look at what we are given. OE is perpendicular to AP. Where's OE? Okay, OE, which is this one, perpendicular to AP. Already I'm starting to write some stuff down. Okay, I have what? If OE is perpendicular to AB, then it means that the line AE should be equals to the line EP, and both of them should be equals to 7 units, because we are given one of them. Why? Same old line from center perpendicular to a chord, like that. All right, and then from here, what is it that we have? Let's look at the other part. OE is equals to 24 units. Okay, there's OE. And what is it? And DF is equals to FC. Where's DF? DF is this line right here, which is equals to that. But wait, they just told us that this line, look at the line that is drawn from the center. This line runs from the center all the way to that chord, but it goes through the midpoint. It cuts the chord into 2 equal parts. So we can make a conclusion, right? Remember, this is the converse now, which tells us that OF will be perpendicular to DC. Why? Because now we have a line that is drawn from center, but it goes to what? It goes to the midpoint of a chord, midpoint chord. So with this information, then we can start calculating some stuff. They want us to find AO first. As you can see, on A, to find AO, we have to use that triangle that contains AO, which is this one. Pythagoras theorem comes to our rescue again, because we have a 90 degrees there. As you can see, this angle AEO will also be 90 degrees on angles in a straight line. So let's try that. Having this, having that, and lastly this. So when we do that, we are going to have O, we are going to have A, we are going to have E. That's 90 degrees. We have a 24 here, and then we calculated this to be 7. Pythagoras theorem, find the hypotenuse, draw a diagonal, extend, then you get there, which means OA or AO is your hypotenuse. So AO squared is equals to OE squared plus what? Plus AE squared. And this comes from the Pythagoras theorem. Do we have AO? No, we are looking for that. AO squared, which is equals to OE. OE is 24, so that's 24 squared plus AE, which is 7 squared. This should give you 625. So AO squared is equals to 625. But we are looking for AO, square root both sides. So AO should be equals to the square root of 625, which is 25 units. There you go. So you have that as 25 units. And once you have AO as 25 units, you have OD. OD is equals to AO, and they are both equals to 25. Why is that? This is already I. So at least here we have 7, we have 25, we have 25. Right, so we found AO. They want us to find what? OF. We need to find OF. Okay, let's try to set up our triangle there so that we can use Pythagoras. Remember, DF is equals to FC as it's given in the statement, but FC is 15, so both of them should be 15 as given right there. So here we have 15. Remember, we just made a proof, something we proved in the opening statements, that actually we have a 90 degrees here. And once we have a 90 degrees, this allows us to use what? The Pythagoras theorem, like I said. This theorem 1 is very dependent on the Pythagoras theorem. Okay, so we have that, then we have this. It looks something like that. Right, so you have a 90, you have F, you have D, you have 15, and you have 25. You are looking for OF. Again, Pythagoras. Go to your diagonal, draw a line, then you have it there. So our hypotenuse, which is OD. So OD squared should be equals to OF squared plus DF squared. Why? Because I'm using the Pythagoras theorem. And then what else now? OD, I do have OD. OD is 25. So that's 25 squared, which is equals to OF squared plus DF squared, which is 15 now squared. Then we try to expand that, but in the end you are going to end up with OF, which is equals to the square root of 25 squared minus 15 squared. You can do it step by step, but you should pretty much get it now, which is 20. So OF is equals to 20 units. Right, now last question. I'm gonna erase this. They wanted to find FG. Look at FG. Which is that? FG is right there. Okay, to find FG we need OG first, but remember that OG is also a radius. OG is the same as AO or OA and is the same as OD, and they are all equals to 25. This is a radii. like that. And now look at the line OG. Right, the line OG, which is that red line, is something like this. You have O, there you have F, and lastly you have G. You have the total length of these to be 25. You just calculated OF to be 20. So think about it. OG is equals to OF plus FG. It's made up of those two smaller parts. The total length is made up of this small piece plus that small piece. So this is 25, which is equals to OF, which is 20 plus FG. So by default, you can see that FG should be none other than what? Than 5 units. Okay, I hope this makes some sense. And now to the last part, which wants you to use variables. Okay, here you go. DC is perpendicular to AB. Where's DC? Okay, DC, that whole line right there is perpendicular to AB. Okay, I'm already starting to make some conclusions. If that is perpendicular, then it means AE should then be equals to AB. Why? Line from center again. We have a line that is drawn from the center of the circle. Line from center perpendicular to a chord. Okay, and then let's move on with the statement. I've used this and cut AB at E, right? DE is 18 units. Oh, so that whole length right here, this is 18, and AB is 24 units. Okay, AB, which is this one. So AB is going to help us. Remember, we said AE is equals to EP, but since we have the total length of, we know that these two, AE and EP, are supposed to cut 24 equally, right? So this means each one of them will be 12 units. We don't need a reason because this is a substatement from our opening statement. And by default, we've just answered 1.1 because they are looking for the length of AE. So let's proceed to 1.2. If the radius of the circle is x, which means you have x here, this will be another x because that's also a radius. And I say another radius, which is the line O. Has to be the line OC. This is another radius, which is x, but I don't want to use that. Let's just stick to those two. Right, determine what? If the radius of the circle is x units, express OE in terms of x. So they want OE, this small part, in terms of x. But wait, look at that line, the total line of what? Of DE. So you are starting from D, you go to the central point, which is O, then you end up at E. We do have this total length to be 18, and we have the radius DO to be x. So think about it. DE, the total length, is made up of those two subparts, which is DO when added to what? When added to OE. No reason needed for that, right? But DE we have to be 18 as given in the statement. Do we have DO? Yes, DO is a radius, which is x, plus OE. And by default, you can see that when you transpose this, then OE will be equals to 18 minus x. They said find it in terms of x. You just did. Calculate with reasons the value of x. Again, Pythagoras theorem comes into action. Remember, this one we found to be 18 minus x. This one we found to be 12. So now it's complete. If we look at our triangle, we have something that looks like that. Okay, we have something that looks this way now. I suck at this. We have a 90 degrees there. This is O, that's A, and that's E. What kind of an E is that? That's E. So this is 18 minus x, that's x, and that's 12. Pythagoras theorem, identify the hypotenuse. There's my hypotenuse, which is AO. So AO squared will be equals to AE squared plus OE squared. Why? This is Pythagoras theorem. Do we have AO? Yes, we do. That's x, but that x is squared, which is equals to AE. Do we have AE? Yes. AE is 12, right? So that's 12, but it's squared. Do we have OE? Yes. That one is 18 minus x, but it's also squared. So this is x squared, which is equals to 12 squared is 144. Plus, when you expand that, now what is 18 times 18? Which is 324. So we have 324. Remember now, here's a most common mistake that people make. They tend to say that 18 minus x all squared, you can just distribute this, and this is not just wrong, this is very wrong. You need to open two brackets. You cannot say this is 18 squared minus x squared, but this simply means that it's 18 minus x into 18 minus x. Then you use the FOIL method to expand that. normally. So as you can see, when I use the FOIL method, 18 times 18, I'm getting 324, right? And then when I say 18 times negative x, I'll get negative 18x. Again, negative x times 18, which is negative 18x, and that gives me minus 36x. Lastly, minus x times minus x, which is positive x squared. There you have it. You see, avoid those mistakes. And then finally, now let's just transpose this one to that side, which means we are going to have x squared, that x squared, minus the one we just transposed, and then we have minus 36x. And then what is 144 plus 324? And this should give us 468 plus 468, which is equals to 0. This cancels that. Then we have minus 36x transpose the minus 468 divided by negative 36 divided by negative 36. So what you get finally is what? 468 divided by 36, which is 13. So x is equals to what? X is equals to 13. Then you have your radius. Your radius is 13 units. You have your length of OE. And that is how you apply these two theorems. Right. There's another one which the proof is not usually examined. It states what? The perpendicular bisector of a chord passes through the center of the circle. So technically what it means is what? It means that if you have those, let's look at this one. That chord right here, and then you have just a random line there. Okay, which does what? Which meets the chord at 90 degrees, as you can see. Right, what this means is that this line shall pass through the center, passes through the center. Well, the application of this is very minimum, but you need to know it. Passes through the center like that. Okay. So now try this. This is an exam question and it's a proof. Use everything that we spoke about. This should be easy.